Hey everyone, today's video is going to piggyback off the last one I made, which was distributed loads and how to combine them. Today we're going to talk about distributed loads by integration. So basically the same concept, just a little bit different. So for this example, you'd have a problem like this, where your beam is being acted on by a distributed load that is non-uniform in any way, shape, or form. The only way that we can do this is if we have been given a equation that represents this distributed load. So we're going to say that this is, the equation for this is y equals x squared. Okay, so that equation describes this line right here, given that this is our x-axis and we have a y-axis right here. So the way that we do this, you already could have guessed, is by integration. If we go back to the last video when I was talking about how you can think of this just as geometry and finding the area of an object, well, how do we find the area under a curve? Well, that's by integration. So that's exactly what we're going to be doing here, except for we're not really finding area, we're finding forces. So we're going to replace this distributed load with one force acting at a certain distance. We don't know what that distance is yet. So, how do we find the force? Well, we just integrate. Force equals the integral of x squared evaluated from 0 to 3. Okay, so integrate that, becomes x cubed over 3 evaluated at 3. So 3 to the third, 27 divided by 3 equals 9. So our force equals 9 pounds. Okay, so force wasn't too bad, just integration. Going back to calculus there, the distance that this force is acting at is a little more complicated though. First, we have to think of centroids. And if you've already done the centroid section, great, this is going to make a lot of sense. If not, this will make more sense after you do the centroid section. So let's look at this for a second. If we have a triangle, the centroid of our triangle is going to be somewhere in here, right? And as we talked about last time, that is 2/3 of the distance from the smaller end. So that is where we put the force. When we have a rectangle, our centroid is directly in the middle. So that's where we put our force for a rectangle. Basically, it's the same with this. We need to find the centroid acting in the x direction, so we don't really care about how high up the centroid is or it is in the y direction. We just care about the x direction. So we're going to say the centroid is located somewhere in here, and then we're going to put the force right there. So to find the centroid, you do the sum of the distances times the area divided by the sum of the areas. Basically what that means is if you have a bunch of different objects, you're going to sum up all of their areas and put them there and there, and then you're going to sum up all of the distances to their own individual centroids and put that for D. So basically if you had a square and a triangle, Well, the d for the square is this distance right here, acting halfway. The d for the triangle is going to be right there. So you just add all those together and then do this. Now, when we're doing integration, what we're actually doing is taking a bunch of infinitesimally small elements and we're adding up all of their areas. So we've already added up all of the areas, which is how we got this 9. Now we just need to find the distances. And the distance of that super small sliver is just going to be x. So hopefully that made sense. Stick with me. To find x, in this case, the distance we're putting that point, we're going to do the integral of x times f of x divided by the integral of f of x. Okay, so the sum, remember, integrating is just summing up a bunch of small things of the distance times the area divided by the sum of the areas. So it's the exact same thing. And in this case, our equation is just going to look like this: x equals, actually let's call this x bar to distinguish between these two, is going to equal the integral from 0 to 3 of x times x squared divided by the integral of 0 to 3 times x, or of x squared. So we already know that this equals 9. Let's make a little more room here. I'm just going to do it over here. So x times x squared is x to the 3rd. If we integrate that, we get x to the 4th over 4. That's going to be evaluated at 3. And then we have x to the 3rd over 3 evaluated at 3. Anyway, we can just substitute these two out and evaluate from 0 to 3. So plug a 3 in for the x's, and we just go from there. So this should equal 20.25 over 9. So our x distance over here equals 2.25. Anyway, so that's basically it for solving distributed loads with integration. We now have replaced this object with our more simple one here that just has a force and a distance from this point A that force is acting. Anyway, that's it for today. I'll see you guys next time.